Hi everyone. Today, we're diving into why computer scientists are fascinated by the P versus NP question and how it impacts real-world problems like security and AI. Every time you try to schedule many tasks, plan deliveries, or tune a complex system, there is an invisible rulebook predicting which ideas will scale and which will blow up on you. That rulebook is the world of P versus NP, and by the end of this mini lecture, you will see how it tells computer scientists which problems are manageable and which are ticking time bombs. We will build everything from familiar ideas about algorithms and growth. No heavy math, just the difference between slow and impossible. First, we will compare polynomial and exponential growth, then see how NP-complete problems secretly share one difficulty class, and finally, look at worst-case cliffs and why this shapes security, AI, and optimization.
Last time we talked about P versus NP as a big math question about existence and discovery. So now we are switching to how it affects actual code and systems?
Exactly. Today is about the computer science worldview, how this one question predicts which problems scale, which ones explode, and why so many different tasks feel hard in the same way. In part one, we looked at P versus NP as a philosophical puzzle about whether finding solutions is really harder than checking them. Now we care less about philosophy and more about scaling. As the input size grows, does the work stay manageable or blow up so fast that even supercomputers give up?
So P versus NP is kind of a forecast for whether your algorithm will ever handle real-world sizes?
We will take the working computer scientist point of view where P versus NP guides what kinds of algorithms you even bother searching for. We will zoom in on growth rates, then the unifying idea of NP completeness, then the worst case cliffs that hit solvers, and finally what all this means for security, AI, and optimization.
I am especially curious about that idea that totally different problems like routing and scheduling are kind of the same under the hood.
Perfect, because once we see how growth works, we will be ready to meet NP completeness, the reason so many hard problems share one difficulty rating. To a computer scientist, hard usually does not mean clever. It means how fast the running time grows as you add more input.
So it is less about a single tricky puzzle and more about what happens when you scale that puzzle up?
Here are two stylized running time functions, one that grows like n squared and another that doubles every time you add one more item. Think of n as how many cities in a route, how many tasks in a schedule, or how many variables in a formula. Polynomial time means the work is like n squared or n cubed or some fixed power, which may be slow but usually still usable if you throw hardware at it.
So doubling n might mean 4 or 8 times more time, which is annoying but still in the realm of possible.
Exponential time is the nightmare zone where each extra item multiplies your work by a constant factor. So going from 20 to 40 items turns a million steps into around a trillion.
Right, that is the cliff where at some size it is, not just slow, it is basically never finishing in the lifetime of the universe.
The class P is the problems that stay in this manageable polynomial world, and P versus NP is asking which kinds of tasks escape into that exponential explosion. Now we add one more ingredient, not just how fast we can solve a problem, but how fast we can check a proposed solution.
This is that idea from last time where NP means you can quickly verify a solution if someone hands it to you, right?
First, any problem we can solve quickly. We can also check quickly, so P sits inside NP. NP is the big class of problems where if I give you a candidate answer, you can confirm it is correct in polynomial time. A classic example is satisfiability, or SAT, where you ask if there is some way to fill in true and false values that makes a big logic formula come out true.
And if someone gives you a specific assignment, you can just plug it in and check quickly whether the formula really becomes true.
Cook and Karp show that SAT and many other famous problems are NP complete, meaning every problem in NP can be translated into them with only polynomial overhead. So if you find a truly fast algorithm for any one NP complete problem, you have effectively solved all of NP efficiently.
So that is why scheduling, routing, packing, and all those feel similar. They are all different costumes for the same NP-complete core.
Exactly, and that shared core is what lets one theorem about NP completeness explain thousands of real-world hard problems at once. Here is the confusing part. If NP-complete problems are so scary, why do modern solvers handle many real instances just fine?
Yeah, we have SAT solvers, route optimizers, and scheduling software that work in industry every day.
In practice, we throw powerful heuristics and clever data structures at these problems, and for many industrial cases, they return answers in seconds or minutes. Most real inputs have patterns like geographic layout or regular schedules that make them much easier than a totally arbitrary worst case.
So even though the problem class is scary, the actual instances we see every day are often friendly.
But NP completeness is about worst cases, and there are inputs where one small change makes a solver go from seconds to centuries. In adversarial settings like cryptography, an attacker is actively trying to craft those cliff edge cases to make your algorithms grind to a halt.
So NP completeness does not say every input is awful, it says you cannot design one algorithm that is guaranteed to avoid the cliff for all inputs.
Exactly, and that gap between typical and worst case is why engineers can often cope, but theorists still warn about fundamental limits. Now that we see how NP complete problems behave, we can talk about why P versus NP underlies so much modern technology. Encryption schemes like RSA rely on the idea that some problems are easy to check but believed hard to solve, such as factoring large numbers.
So if the hard part suddenly became easy, all those secrets would be exposed.
If P turned out to equal NP, many of these underlying hard search problems would have efficient algorithms which would break most current public key cryptography. Machine learning and combinatorial optimization often mean searching an astronomically large space of possibilities for a good configuration or schedule.
We use greedy methods, gradient descent, and lots of hacks, because finding the absolute best is usually in that NP hard territory.
So if P equaled NP, perfect optimization would become routine, but our cryptographic safety net would vanish. If P does not equal NP, secrets stay safe, but we live with approximations.
That is wild. The same hardness that annoys us in optimization is exactly what protects our data.
Let us imagine the two possible universes complexity theorists talk about and what everyday computing would feel like in each. In a P equals NP world, any problem where you can quickly check a solution can also be solved quickly. So perfect scheduling, routing, and design become routine.
So your laptop could spit out the optimal exam schedule, delivery routes, chip layouts, and maybe even perfect neural network weights.
The price is that any system based on easy to check but hard to find secrets, like passwords or public key encryption, would become breakable almost instantly. In the more widely believed P not equal NP world, some problems truly resist all polynomial time algorithms, giving us strong foundations for cryptography, but permanent limits on exact optimization.
So we get to keep secure communication, but we have to accept heuristics and good enough as a fact of life.
Almost every expert bets on P not equal NP, but we do not yet have a proof, which is why this question still haunts both mathematicians and computer scientists. Let us zoom out and connect the dots between scaling NP completeness and real-world impact. First, the line between polynomial and exponential growth is the line between slow but feasible and basically impossible beyond modest sizes. NP-complete problems form a single difficulty hub, so solving any one of them efficiently would unlock efficient algorithms for thousands of others.
That is why scheduling, routing, planning, and many puzzles all feel like different faces of the same beast.
Complexity theory does not forbid solvers that work well on many inputs, but it warns that no single algorithm can avoid horrible worst cases if P does not equal NP. Modern cryptography implicitly assumes P does not equal NP to keep secrets safe, while AI and operations research accept that heuristics and approximations are here to stay.
So P versus NP is not just a $1 million math puzzle, it is more like a map of what algorithms can realistically do in our universe.
Exactly. And once you learn to recognize NP hard structure, you know when to stop hunting for a magic exact algorithm and instead reach for approximations and heuristics Before we wrap up, let us do a quick check you can answer and a reflection to tie it back to your own experience. First, think about the decision problem where someone hands you a complete tour and asks whether its total length is at most some target value.
We are not searching all tours ourselves, we are just checking one given tour against a distance limit.
Exactly, you can add up the edge lengths once and compare to the target in polynomial time, so that specific checking problem sits comfortably in P and therefore also in NP, but it is not NP complete by itself. Now, think of a time you faced messy scheduling, packing, or tuning in real life or in code and ended up using rules of thumb instead of a perfect solution.
I am definitely going to wonder now whenever I see a stubborn optimization problem whether I am bumping into NP hardness rather than just being bad at coding.
That is the perfect mindset. Recognize when P versus NP is the real obstacle, lean on heuristics without guilt, and if you ever do prove P equals NP, maybe warn the security teams before you celebrate.
Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.